Let me tell you about how we were able to improve both performance and availability to the cloud for thousands of networks. I'm going to first tell you about a changing enterprise landscape. Before, enterprise services were hosted locally on their own networks, and then enterprise managed everything, which was nice because everything was under the control of one domain, but it was also inefficient and expensive to upgrade. Whereas now, services and software are increasingly hosted in the cloud, and employees are increasingly remote, which is nice because it's a much more flexible solution with each party focusing on their strengths. However, we now have this heavy reliance on an internet connection. So what do I mean by that? Well, look at this picture of an enterprise accessing services in the cloud. Notice that the path to the cloud goes through the public internet, and neither the enterprise nor the cloud have a lot of control over that path. For example, if the path to the cloud fails, they don't know which backup path it will take, and they don't know if that will be performant. So it would be best if clouds could place traffic on performant paths at all times, but cloud's ability to do this is frustratingly limited, especially given the rich connectivity available to clouds. Clouds often peer with thousands of networks at hundreds of pops, which means that even single networks have many paths to many pops. However, clouds have to contend with BGP and DNS to place traffic on paths to the cloud. For example, let's say a client wants to access a service and that service gets translated to some hostname, service.com. That client will query the DNS. But that DNS resolver might serve many networks, not all of whom share the same best path to the cloud. Moreover, returned IP addresses are cached, often for much longer than clouds want them to be. Actually, in a study of more than 500 residential units, we found that more than 90% of bytes were being sent to Azure using expired DNS records. This severely limits the speed at which clouds can place traffic onto new paths. Clients will reach out to returned IP addresses, and although there might be many policy-compliant paths towards that corresponding IP prefix, BGP only selects one. And that path might not be the most performant path, nor does it change with changing performance or congestion. Well, why haven't clouds done much to get around this? Well, quite simply, it's pretty hard to get around BGP and DNS. Clouds have to deploy solutions in hundreds of thousands of client networks. Moreover, clouds can't simply just expose every path to the cloud because there are too many paths to expose. Paths are exposed with IP prefixes, but IP prefixes have a cost. So clouds need to choose some subset of paths to expose. But advertising a prefix to expose one good path might also expose another bad path. In the following slides, we're going to discuss how we solve these key challenges. One interesting observation is that enterprise networks follow the common deployment model. With traffic from the network going out to the internet, they have these network appliances that sit in the middle, enacting fine-grained policy on user traffic. For example, load balancing traffic among their various internet service providers, or treating different service traffic in different ways. And enterprises configure these appliances using frameworks that are integrated with the cloud. Our observation is that clouds should manage these devices on behalf of the enterprise network, therefore giving themselves fine-grained traffic management capabilities. This is in addition to the fine-grained traffic management capability they already have in their own networks. Well, so now let's say we adopt this deployment model for so-called Painter edge nodes, the edge component of Painter, and that these nodes give us, that is clouds, the capability of putting traffic onto different available paths at fine granularities. The question is, well, which paths should Painter expose? And this is a challenging set of paths to compute because it has to optimize over hundreds of thousands of networks with tens of thousands of paths and peerings to choose from. So how do we do this? Well, our first observation is that different paths to different peers and providers have different performances. And by only advertising to those peers and providers, we limit the set of paths BGP has to choose from. So here we're only advertising to the two peers and providers shown in orange, and so only those paths are revealed to Painter edge devices. The second key idea is to advertise this prefix to as many peers and providers from as many POPs as possible, exposing the maximum number of good paths to client networks that we can with just a single prefix. One problem this introduces is the following scenario where this client has the circuitous route to a distant POP because BGP just isn't performance aware, it exposes this path to this client. To get around this, we try to observe when these instances occur, and we compute new strategies that avoid such cases in the future. For example, maybe a way around this instance is we advertise instead a different prefix closer to the client, giving that client a low latency option. So we use these three key ideas to compute advertisement strategies. And using these three key ideas, Painter Cloud, the second component of Painter, advertises prefixes to its many peers and providers, giving Painter Edge devices low latency options from choose from. Painter Edge devices then measure to and dynamically place traffic on the best paths at each moment in time. Painter, therefore, is the combination of this fine-grained traffic management at the client edge, coupled with intelligent prefix advertisements from the cloud. We want to deploy Painter using the peering testbed, which is now on Vultr Cloud. This testbed on Vultr Cloud is available for everyone in the community to use. Vultr lets tenants advertise their own prefixes to more than 10,000 peerings at 30 POPs. And so shown using purple stars are the POPs that we deployed Painter on, and in orange are the client networks that we probed. By changing the way we advertised real BGP prefixes into the real internet, we were able to change the paths that real client traffic took. We're going to show how we use this deployment to provide both maximum performance and availability for a single edge network. So Painter Cloud went and computed the best paths to expose, and it advertised those prefixes into the wild. Shown on the latency time series graph are measurements towards these prefixes from the Painter Edge device. The Painter Edge device dynamically measured the different prefixes and saw that the red one was offered the lowest latency, and so it placed traffic on this path. In salmon is the Anycast path that Azure already advertises to the world. But let's say that, and what we did is we simulated a POP failure, that this close POP that this Painter Edge device is visiting fails, and those paths no longer become available. What we're going to do is we're going to compare Painter's capability to provide availability to other options that clouds use. Anycast suffers from about 1 second of unavailability, followed by 30 seconds of instability due to BGP reconverging. That's shown using the changing latency in the time series. DNS, another common option clouds use to switch traffic to new POPs, would be unavailable for about 60 seconds due to DNS records staying in caches, and so clouds can't update the IP address that clients use. This Painter Edge node is always dynamically measuring to these different prefixes. It's looking for failure, and it's realizing that this path fails, so it switches traffic over to the backup blue prefix path within an RTT. So Painter is providing both maximum performance and availability faster than current methods, Anycast and DNS. So we prototyped Painter with this global testbed deployment on Vultr, and we used this prototype to demonstrate that we can improve user latency by an average of 60 milliseconds for thousands of networks using fewer prefixes than other methods. And we also demonstrate that Painter provides fine-grained redirection at per-flow granularities and RTT timescales. We have many more results in the paper, and you should definitely check those out. But stepping back a bit, clouds before were optimizing in the intra-WAN and egress traffic engineering settings because in those domains they had full control and they could use that control to improve performance for their applications. But now we've got these new applications and use cases that are going to demand better performance than BGP and DNS can offer. So clouds need to extend their control. And actually what we show in this work is that clouds can overcome those limitations of those previous protocols using their increased presence at the client edge so that they can now offer that new performance that these new applications and use cases demand.